Let's welcome Tigran Nazaryan from 10 Web. He's a team lead of R&D and VP of Engineering. Hello, Tigran.
Hello. Hi all. I'm just gonna share my screen right now.
Screen.
Okay. Do you see it? Is voice quality okay?
Yes, everything okay.
Okay. So let's start. Today I'm gonna talk about usage of machine learning in creating tools for web developers, particularly website builder and assistant based on AI. And for that, we need to learn semantic structures of web pages. Just a couple of words about the background problem. This is quite an important problem for web developers to automation of front-end creation. I mentioned here 6 stages of typical web development process, from the defining architecture to the final release. And an important part of that, which is quite routine, boring work, it's creation of front-end. That is pages, coding HTML or doing it another way. And there is a way which is much better than just coding plain HTML, which is recently became very popular, and a lot of software uses that. It's the group of software or programs called page builders or site builders. These are used by many popular CMSs such as Wix or Squarespace, and WordPress, the most popular CMS, actually has many page builder type plugins which have one common feature. Instead of writing HTML, developer or designer just takes blocks with semantic of certain types, adds that into the page and drags and drops them, or creates columns, sections, or customizes that. So this allows spending much less time for building front end. However, also this is quite routine work and there is a large room for automation. So as a company creating products for web developers, freelancers, agencies, we thought about creating solving this particular problem, that is how to create a website that looks like the original input web page. But just don't copy the code, but understand its meaning, its blocks, and create a similar page with semantic blocks, which are very easy to customize. And there is an underlying machine learning problem. That's classification problem of web page elements in terms of that types of widgets of builder software. By saying types of widgets, I mean things like this. Here we have logo, menu, text, button, image, and some of types are quite simple, for example, image. But other types can be complex and contain many parts, such as call to action. But this has just one meaning, or gallery, or pricing. So we're going to find out how can we classify parts of web page, which is HTML, and it is tree-like structure, that is 3 nodes. How can we classify 3 nodes in terms of that builder? And there are 2 approaches that can be implemented. First one is being based on screenshot. That is, we feed screenshot, image, and try to find, to extract code out of it. And of course, there are many solutions for image classifications, image processing, but all these are quite complicated things. And for this particular problem, customizing some standard approach, it will add additional complication and complexity that we want to avoid. Also, we need to take into account that actual screenshot contains less data than HTML or web page itself. First of all, it's obvious that it doesn't have animations and all these dynamic parts, effects, so we lose them. And the second, that web page itself has more data. So each element has some meaning, and transferring that to the screenshot, we lose data, and we make extracting data out of screenshot harder. And also using a tree-to-tree approach, that is from HTML tree to the final tree, it allows us to avoid OCR, implementing OCR solution on top of image processing, this general solution. Here is the particular example. On our left side, we see HTML. It's just HTML. And on the right side, it's typical output for a page builder solution. This is also, usually it's tree-like solutions. And here we have a tree which can have a depth until 6. That is section, column, below it, one more section and column, perhaps, and widget or block. So actually this is classification problem, or we can say it's translating web page into the language of higher level semantics, because each element in web page, it is less meaningful than a composition of that elements which is classified in terms of blocks. So this is the problem we're gonna solve using machine learning techniques. But the actual problem, the most difficult part, is not the classification itself, but as usually happens, data collection, data processing, and preparation of data. So our team spent around 2 months for this, creating a good data set. And we are 5-6 people. So we see that it's a quite large, time-consuming work. Another important thing, that tools are needed for data collection. That is, even it's plain HTML, we need tools to extract meaningful data out of it, and I'm going to talk about it a little later. Very important problem is that web pages are not static, so we have built a caching solution which basically saves web page, including its resources such as style, script, images, videos, and we can say detaches it from its from connecting to its web server, so that we cached our data set web pages. Our solution is for landing pages mostly, because this is the area which is needed to be automated. Like marketing agencies, they can create tens of web pages every day for landing pages to make some A/B tests, let's say. So this type of pages particularly is more important. And there is data balance problem, because of that widgets, some types are quite rare and it's quite difficult to find corresponding pages containing such types. Here is the procedure. We took an Alexa top billion sites. We filtered in our final list a data set of around 500 web pages with their elements, and we use them to train data using supervised learning. And the final solution also creates a database of pages, nodes, and corresponding labels. And all this is integrated through the API with the Chrome extension, which is actually the tool we are using for manual classification. Here is some problems that we need to solve. That is, we need to pre-process web pages to prepare them before running machine learning algorithm. Some websites have protection from crawlers, bots, or malicious visitors, and we need to find a way to overcome such protection. Of course, we are not malicious, but they can misclassify us as malicious bots. A page may just trigger a pop-up alert or think that some part that makes problem, so we need to close them, remove them. Another problem is related with animations and effects. We need to find a correct value of moving element parameter. For example, we need to either freeze that animation, or we have to find a, let's say, correct position or the best value of position for such an animated element. Some elements need to be adjusted, I mean their geometry. For example, let's say we have a link which has 0 size, 0 height, 0 width, but it contains some subtree, some text. So we need to stretch it to contain all the subtree. And an important part is restructuring the tree according to the visual hierarchy of the nodes in that tree. Look at the right side picture. On the first part, we see red node as a leaf, but on the right part, red node was restructured to be a container of green and yellow nodes. So what does it mean? It means that the element corresponding to the red node is visually overlaying or underlaying and is larger than all these green and yellows elements, so it contains them. So we need to restructure the web page so that it reflects its visual appearance. Here is our extension we use for manual labeling. This is Chrome extension, and we use it just it's quite intuitive. We just click on top of element, and it pops up. It opens a pop-up with choice of a corresponding label. On the left side, you see the restructured tree of that web page. And on the right side, you see feature vector components. And we didn't label all the elements in web page, because web page may contain a lot of headings, but we need such an amount of headings. But instead, it's good to find another web page which contains pricing. So this way, we try to solve data balance problem, and I'm talk about one more solution a little later. Important aid can be done for an engineer if we use our previous version of classification algorithm, and it automatically classifies all these elements as a first iteration, and then the human classifies all the necessary elements, or let's say reclassifies them or corrects the classification. So we did this approach, and it helped us to save some time. A final list of feature vector parameters contains more than 40 parameters, and some of them are style-based, and another group of them are geometry-based. And it's an example just. For example, menus are located usually on top of web page or on the bottom, in the footer area or in the header area. So geometry, of course, is very important. One set of parameters we call them local and global parameters. It is, let's say, word count. Word count can be defined either for a single element or cumulative number of words inside its subtree. So both parameters are meaningful. First one is local, the second one is global. Moving to this point, even though HTML is semantic language and tags have some meaning, most of the tags, but the number of tags in HTML is very large, more than 100, and most of them are quite rare, so we simplified this and grouped them to make dimensionality of feature vector less. For example, heading large, as you know, web page headings HTML correspond to 6 tags from H1 to H6. So usually from H1 to H3 are like important prominent headings, and the rest are secondary headings. Class name is another attribute of web element, which also can have semantic, have some meaning. Class name, for example, a developer when creating web page and associating styles with that elements, they apply styles using class names and IDs. So they denote class name in a way that reflects its meaning. For example, if we have a link, it corresponds to the A tag. If it has class name equal to BTN, so it means that most probably this is not just simple link, but it is styled as a button. So we analyzed our final sample, labeled sample. We analyzed the class names corresponding to that labeled sample and added a score to each class name, which shows its correlation or probability to belong to a certain label. This is class name grouping. I don't want to go into too much details. In the next slide, I want to discuss an important point about images. When seeing visually web page, images can be either through the image tag, like this, or they can be visually appear as an image, but it can be a background of another element, or vice versa. We can have a pure background, or we can have an image element which is underlying to some other text, so it works as a background. So it means that just we can take and count images, but we need to understand their geometrical relation with other elements and to see if they are really images or backgrounds or the opposite. Here is the final sample we used for training. It contains around 13,000 nodes and around 20 types or labels. As you see, some labels are quite rare, such galleries or lists, and we used data augmentation to create more of them. How it works. For example, data augmentation according to the geometry. If we have an element which is classified as a gallery, so most probably it means that we can move it back and forth, higher or lower, and it still remains a gallery. So this way we create more galleries by augmenting its geometry. The same way we can augment other parameters according to the distribution of that parameter within some constraints, of course, to create more of such data. Since data collection is time-consuming, we try to have as simple model as possible to avoid spending months for data collection. That's why some types cannot be classified using such a machine learning solution, because they are either too complicated or too rare or because of other reasons. For them, we have created some custom classifiers, and this way we avoid over-engineering our machine learning model just for the sake of one label. We use three types of machine learning models: SVM, random forest, and DNN. We started with SVM, and our latest solution is DNN-based. Regarding the precision or performance of these models, I would say that they are not much different. DNN is a little better than random forest and SVM, but not much better. For such number of data points, simple DNN structure is enough. And here is the structure of our DNN. It's 3-layer, just standard network. And our results for training, we see that F1 score is, on average, is 0.87 for DNN, which is quite good, or good enough, taking into account our problem. Of course, not all types or all labels are classified with the same precision or recall, but we need to find a good balance. Why? For example, when having pages, pages usually contain much more headings than pricing tables or pricing lists. That's why we can have trade-off. For us, it can be more important heading classification than pricing classification. We analyze feature importance using two methods for random forest, and we assume that similar importance is valid for the DNN as well. This helped us to reduce the dimensionality of feature vector space. And here is the confusion matrix. After classification by the DNN and other algorithms, we applied additional label conditions. This helped us to avoid over-engineering our model. Because if you have less data, you can't make AI or ML doing everything. It's better to restrict that data or select and deal separately with edge cases. So our extension for Chrome, it just checks for label conditions as well. And if human classifies them by violating label condition, it pops on an alert. One fundamental limitation of this model is that we classify each node inside tree separately. So although we have some parameters which are context related, for example, number of children or number of similar siblings, but generally we can say that this is an important drawback of that model, because we don't have information about context of each node. That's why we apply additional logic after machine learning and label conditions. We call reclassification, which is set of some rule-based algorithms which takes into account how other elements were classified inside that web tree. For example, if a node is classified as a container, all the elements above it, we also classify them as containers. This helps us to get a correct result. That is, we have containers above and meaningful widgets or other types below. And this problem can be solved by using recursive neural networks or other type of solution which is context aware or which has some state information depending on the context, so that we can train it moving back and forth of the tree. However, this will require much more training data, and we don't think that it is effective or it is necessary to implement it right now. Also, let's take the full pipeline. Machine learning is just one part of it, point number 2. But the whole pipeline for website creation is as good as the worst part of it. And the most complex part is not machine learning, but the most complex part is building layout. It has few parts. One of them is how can we choose which widget is the actual widget. If we have classified each node in the tree, we can either select parent node and say this is our final widget, or we can get rid of it and select its children and have two separate sub-widgets or two separate widgets. So we need to choose them, and we need to recreate a layout within some constraints by final solution that's builder software according to its rules. For example, for the software we use, it's Elementor, it's the most popular WordPress plugin. It can have only four levels depth. That is section, column, one more section, and one more column. So we need to take this into account. And this is the most interesting part, I would say. And this is not machine learning, but it's very interesting AI and a lot of rule-based algorithms that we can talk about that separately. Our product is actually ready, and we are going to release it very soon during the next weeks. and we will offer some deals for early adopters, and we started a huge marketing campaign to feature it prominently. Thank you very much.
Okay, thank you, Tigran, for presentation. Do we have questions?
I will ask a couple of questions. So, first of all, this is like very strange problem, and it's interesting how you approached it. Basically, you managed to annotate 500 pages and end up with how many? 13,000 notes?
13,000 notes, yes.
So basically, you do not use image features, you use manually extracted features from HTML3 and pass it to DNN or SVM, right? Did I get it right? Did you hear my question? Or
I didn't hear the last sentence.
my question was, so basically you do not use image features, you use only manually extracted features from the HTML3, and that's the
Exactly,
input.
yes. Yes, sure. So we avoided image processing algorithms.
Okay, so this is a great example for custom, for a problem which requires custom augmentation. So
right.
We all are used to the cases when augmentation is something that you can download from some library and you can apply it to your images, but here you have to invent everything for yourself.
Yes,
so,
actually we invented everything from the scratch, and even tools for collecting data because there is no data set.
I see. So I want to understand this part better. So when you say you want to change the geometry of one object, so what do you do actually? You change your HTML, the existing HTML code and re-render it through Chrome, or?
No. Since we need just one node of that web page of the tree, and this node, it is just a feature vector with around 40 components. We just augment some components of that feature vector.
Okay, you do the
It's quite simple. It's quite simple. We don't construct one more web page or whatever.
I see. Interesting. You mentioned that you tried to find the best features using this.
Right.
And did it make sense? Like when you look at them, can you kind of understand why these are more useful? Or?
Sure. Actually, we try to discuss what are the features. Let's say this is part of web page. How do I understand that it is menu, let's say? Or how do I understand that it is pricing? Mm-hmm. And it's good to know what these features are, and we try to understand all these features very well.
I see. So with ARIA and the other method gave different top features, right? Font size.
Yes, this is random forest native and permutation methods.
Interesting. And I also wanted to highlight one thing that you mentioned on your slide, that machine learning is not useful for things that are too simple and for things that are too complex.
Exactly. In order to machine learning algorithm to solve this classification of complex things such as slider, we need to make it maybe 10 times more complicated. But we don't want it just for slider. We just searched and went through the most popular sliders and trying to find rule-based algorithm for classifying each one of them.
Okay, and I see there are two more questions in the Q&A window.
Right, let me answer the first one. Georg Minasyan asks, maybe I have missed that part. You mentioned there are two types of approaches, peaks to tree or pix to code and 3 to 3. Why can't we solve 3 to 3 case deterministically without using machine learning? We can. I would say we can, but we wouldn't get enough precision in this case because it's quite complicated for rule-based algorithms. It's quite complicated. Web pages are much more complicated than they used to be, let's say, 20 years ago. It's just not just plain document when you know for sure that H1 is a heading and image is image. That's why we of course, if we could do it, we would do it. And Levan Sinadze asked, did you experiment with graph neural networks for HTML nodes, node classification, for instance? I mentioned about just the DNA, but we didn't go and we didn't search for more complex solutions. And as you can see, our DNA is very simple. Minas Abrahamian asks, how does your solution induce layout HTML tag generation like flexbox, layout flex, or do you generate hard-code position CSS properties? Very good question. We don't want to generate hard-coded HTML. And this is all the beauty of this product. We don't want to generate hard-coded HTML because it is not customizable. So we generate semantic data for import of Elementor plugin. We can do it, of course, for other plugins because they work all in a similar way. They are just tree-like structures where each part of or node of the tree is denoted. Like this is menu, it has these links, it has this color, etc. And we don't need to go deeper to consider how it is rendered.
Okay, thank you. We also have a question from Untitled Chapter.
I don't see it.
He will ask by himself.
Okay.
Yeah, thank you. I will use co-host privileges. Tigran, I wanted to ask about the structural part that you mentioned. So when you just look at the misclassified things, just manually,
Yes.
how much of that doesn't make sense because of the structural thing and could be sort of corrected if a very smart model potentially which was aware of the tree structure was in place?
Okay, I think by saying structural thing, you mean the way the page is coded itself, probably. Because
yes.
Developer can code this page just in using some common sense rules, but they can't code it like this. So, of course, our solution wouldn't work well with coded like this. And we come across so many pages coded so badly that they don't work well. Yeah, we manually inspected all these important misclassification cases and try to analyze them. Is it okay if we can go and continue with that misclassification, or we need to do something about it?
Thank you very much.
You're welcome.
Thank you very much for your presentation, Tigran.
You're welcome.